Welcome. So today we will talk about the physical design. So what do we mean by that is we will talk about the physical storage medium where a database is stored. So we will start off with the cache. Cache, as you all probably know, is very fast. It's faster than main memory, but it's also very costly. And only CPU registers are faster than the cache, but cache is very costly. Data can be stored in the cache, but the more important problem about the cache is that it is volatile. So the contents vanish once the power is off, and it cannot be used to persist a database. The next, we will talk about the main memory. So once more, main memory is quite fast, but also it is again very costly and it is volatile. So the data cannot be persisted in main memory. And what generally happens is that databases are quite large, and the main memory that is available in a machine may or may not be able to store the entire data. Even if it is able to store the entire data, the changes that are made in the main memory are not guaranteed to be persisted, because anything such as power off can happen and the updates can be lost. The next that we will talk about is the flash memory. Flash memory, the USB drives that you use is a type of flash memory, the solid state drive, SSD memory. Flash memory, very importantly, is non-volatile. So what do we mean by that is once you write something to a flash memory, it remains, even if the flash memory is taken out of power or whatever else happens. So it is costlier than a hard drive, and we will talk about a hard drive later, but it is less costly than a main memory or a cache, and it is slower than a main memory. More importantly, flash memory has certain types of has a problem about its read-write cycles. So the flash memory can support only a limited number of read-write cycles. So after about 10 to the power 6 read-writes, 10 to the power 6 is about 10 lakhs, the flash memory performance degrades. So a particular portion of the flash memory may start showing physical degradation, and it may not be able to support any more read-writes. And we'll talk about the flash memories a little bit more detail later. The next important physical storage medium that we will talk about is the magnetic disk. This is the hard disks that you normally understand. Magnetic disks are quite cheap compared to all the other kinds of things, and it can be used to store a large amount of data. It is of course non-volatile, but it is quite slow compared to a main memory, and it is slower compared to a flash memory as well. So after magnetic disk, what comes next is the optical disks. So optical disks are your CD, DVD, etc. And these are also non-volatile. These are also quite slow. But the more important problem about optical disks is, unless it's a rewritable medium, generally CDs and DVDs are write once and read many times. So you write it once and you persist it, and you cannot generally rewrite it, unless of course it is a rewritable medium. The last one in this type of physical storage medium that we will discuss about is called a magnetic tape. So magnetic tapes are really very cheap, and it is extremely slow, because you have to go through a magnetic tape completely to reach a particular byte of data, but it is quite useful while taking backups of an entire institution, or while taking backups of large amounts of data, and it is used very sparingly. And magnetic tapes are generally used only for such backup purposes, not for day-to-day access, because it is extremely slow. So the important parts that we will worry about is the main memory and the magnetic disks, which is the hard drive, and we will also talk about the flash memory a little bit. Now generally what happens is that the databases are generally stored in the magnetic disk. So these are where the databases are stored. But importantly, the operating system cannot access data that is stored in a magnetic disk. So the operating system must bring the data back to the main memory for any access. So the data that is stored in a magnetic disk must be brought to main memory and perhaps more to the CPU registers, etc., depending on the architecture of the machine, but it cannot be accessed directly from the magnetic disk. So there is an overhead involved in bringing this data back from a magnetic disk to the main memory, and this is what is called the disk access time. Now before we analyze what the disk access time are, let us first try to understand what the disks are, magnetic disks that we will be talking about. Magnetic disks generally consist of a spindle, and there are certain types of cylinders attached to it, so certain types of plates attached to it. So these are different plates, and data can be stored on each of these surfaces, this surface and the back surface, so on and so forth, and this is called a platter. So each such disk is called a platter. This is the spindle around which the platters rotate, so essentially everything rotates, and a particular point in each of these platter consists what is called a cylinder. Now how is data stored in a platter? So each platter, if you lay it out, it looks like this. This is a complete platter, of course, with a spindle in between. So platter has two surfaces. On each surface there are different tracks on which the data is stored. So this is one track. So if this is one track, each track is broken up into multiple sectors. So there are different sectors that are broken up. So each of this is called a sector of data. So sectors are separated by gaps, and in each sector consists of multiple bytes of data. So this is how the entire design is there. So each sector contains multiple bytes of data, each track contains multiple sectors, each surface contains multiple tracks, each platter contains two surfaces, and a complete magnetic disk or a hard drive contains multiple platters, and that is how the entire system is there. Now what the OS does is that OS reads an unit of data which is the block or page of data. This is the unit by which the OS reads it, and each sector consists of multiple blocks of data. And having understood this, let us now try to understand what is a disk access time. So a disk access time. So the smallest amount of information that can be read or written from a disk is a sector. So one must reach a particular sector to read. Now what happens is that if we go back to the previous figure, in the cylinder there is a read-write head. This is the read-write head of the disk that moves back and forth across the surface of a track radially. This movement is only radially. So the read-write head, the arm, the head of the read-write arm, this is the read-write arm, read-write arm. The head of the read-write arm can place itself on any track. But having placed itself on any track, it cannot access any sector. So for that, the track must rotate so that the sector is placed under the particular read-write arm, and this movement of the read-write arm and the rotation are all mechanical movements. So that is why there is a physical limit, a mechanical limit as to how much faster a hard drive can be. So coming back to the disk access time, a disk access time consists of three kinds of things. So a disk access time, T access, consists of three different times: time to seek, time to rotate, and time to transfer, and we will describe each of these in more detail next. So the seek time is the time for the arm of the read-write head to place itself on the particular track that it wants to. So it is the radial motion of the read-write head. This is the read-write head, and this is the radial motion of the read-write head. That is the seek time. The rotation time is the time for the disk to rotate such that the particular sector that is needed is placed under the head of the read-write arm. So it can be a complete rotation or it can be a zero rotation with the sector already under the head of this read write arm. So that is the rotation time, and finally is the transfer time. So transfer time is the time such that the complete sector of data is read. So suppose this is the sector of data that is needed to be read by the OS. So this complete time that this rotates such that the entire amount of data is passed under the read write arm. So these are the three kinds of things. The typical seek times are generally of the order of 6 to 8 milliseconds. This is milliseconds, mind you. The rotational latency is, well, we can say it's half the time to rotate on average, because it can be either 0 or it can be a complete rotation. Remember that disks can rotate in only one way. So if the read write arm has just missed it, so it will take a complete rotation for it to back. So it is essentially half into 1 by RPM. This is the revolutions per minute. So to convert it into seconds, need to be a conversion of 60 minutes, 60 seconds. That is the rotation time, and the transfer time is the number of sectors. So if to read one sector, it's the number of sectors per track into that similar 60 by RPM that we will do. So this is the number of sectors that is right. So to read one sector, you require this amount of time, and to convert it into seconds, this is what is being done. So what are some typical disk parameters? So these typical disk parameters, let us take an example to do it. So suppose the rotational speed of a disk is, say, your 7200 RPM, and suppose the seek time given is 8 seconds. These are given by the manufacturers of the disk. Now what is the typical time to read one sector? We can compute it in the following manner. So T seek is your 8 milliseconds, that is given. The T rotation will be, you can compute it using the formula, half into your 1 by RPM, so 7200 into 60, that many seconds. So this come out to be around 4.17 milliseconds. And the T transfer, we can again compute it similarly. So suppose there are 400 sectors per track. So this is 1 by 400 into 60 by 4200. So this comes out to be 0.02 milliseconds. So if we add all this up together, we get a total time of 12.19 milliseconds. So that is the average time to read one sector from the disk. Now as you can see, the disks are quite slow, because to read one sector this requires 12 milliseconds, and this seems to be extremely slow. What happens is that this is what is called the random IO. So there is two important things that we must understand. One is called the random IO, and the other is the sequential IO. What is called random IO is that, if you remember in the last computation, we are trying to read an average time for a sector. So the sector is essentially assumed to be randomly placed anywhere on the disks, and we are trying to find out the time to do it. So that is why it's called a random IO. So you are just given the address of a particular sector and you want to read that. That is the random IO. What happens in a sequential IO is that you are read a particular sector, and the next sector to be read is sequentially placed after that, the sector that you are already reading. So there is no seek time, the seek time is 0. There is no rotational time as well, because the read write arm is already placed on the correct track and just before the sector that is being written. So the only time that is required is the transfer time. So there is a big difference between random IO and sequential IO. So to highlight the point once more, suppose you are reading more than 2 sectors, it makes sense to place the 2 sectors one after another, because to read the 2 sectors, then the first sector needs to be written in a random manner, but the second is just after it, so there is no seek time, etc. The second sector can be read much faster. So it makes sense to put the 2 sectors sequentially on the disk, and that is why sequential access is much fast. That is why sequential access is what is preferred by the database designers. On the other hand, if the two sectors are placed randomly anywhere on the disk, it will take much more time to read the two sectors. So if there is a big large table or a big large database, it makes sense to lay out the data in the database physically in sequential sectors. So that is what the typical thing about this is. So the data transfer rates etc. are computed using this sequential IO time and random IO time and sequential IO time. It actually is a little bit more complicated because there are gaps between the two sectors, but it's roughly taken to be the what we just did the computation. Now one thing to note is that the sequential IO is much faster than the random IO, but much more faster is the main memory time. Okay, but main memory is more costly, so the data is generally stored on the disks only. What is being done is that out of these two, as I already said, most algorithms will try to avoid the random IO time as heavily as possible. So it will rather do a sequential IO time and not a random IO time, because sequential IO is much faster than main memory. One more important thing that the database designers generally take into account is that the time to compute in the main memory is ignored. Why is it ignored? Because the time to bring a particular data to the main memory is so large compared to the computation times in the main memory. So nowadays the machines are gigahertz machines, so it's essentially nanosecond or some orders of magnitude larger than nanoseconds time to do any computation on the data that is brought to the main memory. However, the time to bring the data is milliseconds. So it is, let us say, microseconds as compared to milliseconds. Microseconds on the CPU computation time on the main memory versus milliseconds time to bring the data. So the microseconds time can be ignored, and it is generally ignored by the database designers. So the database designers essentially do not take care of how to reduce the main memory time, because it's only optimizing on the microseconds. It rather tries to tackle more on the milliseconds time and more on the random IO time. So the algorithms are designed so that they reduce the random IO time. This is the one very important point that we need to understand from this physical design, is that the database algorithms are typically designed such that the random IO time is minimized. This was the traditional database story. Nowadays, as we have already mentioned quickly, that there is a flash memory that has come into the picture. So flash memory, it is now becoming cheaper in the sense that some of the databases can be stored on the flash, or at least some portions of the database can be stored on flash, and flash memories are typically faster than hard drives or the magnetic disk that we are talking about. So let us take some typical numbers. So flash drive, the read time for flash can be around, the read throughput can be around 300 megabytes per second. These are typical times. I mean different flash drives will do different. The typical write times are 180 megabytes per second, and flash drives can update, but update is much slower. It can be only 80 megabytes per second, as opposed to disks. Disks are typical read times can be 160 megabytes per second, and write times can be, depending on sequential IO or this IO, let us say about 100 megabytes per second, and update times are essentially just twice of this 100 megabytes per second. So you see there is a cost ratio of about 2 times here, and this can be depending on the whether it's a sequential MB or this thing. So this can be as large as 128 megabytes per second or 64 megabytes per second. So there is again a ratio of about 2 to 3. So flash drives are about twice as fast as magnetic disk, but it is also quite costly. So the database designer can now optimize as to how much data to put on the flash drive. So there is a cost versus access time optimization that the database designers can do. Also flash drives have these problems that data needs to be written in much larger blocks than magnetic disks, and it erodes after 10 to the power 6 read write cycles. So the disk block access that we were talking about, so there are 2 kinds of optimizations can be done about this disk block access. The first is the disk arm scheduling. So what it does is that this kind of algorithm first tries to see what are the sectors that are going to be read or written by the database, and then it schedules such read and write unless they are dependent on each other, assuming they are independent, such that the disk arm is moved from one sector to the another, from one track to the another. So it moves purpose. So first time this data that is sitting on the first track is read or written, then this is accessed, then this is accessed, and so on and so forth, so that there is only one disk arm movement rather than back and forth movements. So that is a disk arm scheduling operation, and then there is an algorithm called the elevator algorithm which tries to do that. Then of course there is the other kind of, this is one kind of optimization, the other kind of optimization is a file organization, and we will talk about this more detail. But the file organization, it tries to do this, we all have seen this term somewhere in the defragmentation. So what it tries to do is, if a file is fragmented, if a file is broken into pieces, then it goes into different parts of the disk. So then there are more random IOs that are needed to read the complete file. Instead, if it is defragmented, the entire file is stored together, and after one random IO, the rest are sequential IO, so that is faster for a database. So that is what it be done. Then there are other kinds of optimizations that it can do. It can use this something called a deferred writes. So essentially the databases use these write buffers. So as soon as a write is available, the database doesn't go and write it back to the disk, it puts it into the write buffer, and only after sufficient writes have been buffered, it then goes ahead and writes them one after another sequentially in the thing. So this maintains logs, etc., and we will see how this is done later, but that is the basic idea, is that it is, the writes are deferred, it's not one after another, it's not immediate, that's the main point. Fine, and then let us talk about a related issue which is on data redundancy. So data redundancy. So data redundancy is done to improve the reliability. So instead of storing the data in only one disk or one place, it is stored in multiple places, such that even if one copy is lost due to some mechanical problem, etc., it can be retrieved from the other things. And there are this famous term of called RAID. So redundant arrays of independent disks. So this is essentially independent, the disks are maintained independently and each one is a redundant copy of the other. Then this mirroring is allowed, and you have probably heard the term in terms of web mirrors. So the entire website is mirrored or shadowed so that one can access it from any of those sites. This is more or less all about the data redundancy. Then there are these problems of how to store the files, the issue of file organization. So the file organization. The files can be stored in a sequential manner, or it can be hashed depending on the block address, etc. So the database stores the data actually about the data, then it also stores something called the data dictionary or the system catalog. Which stores the data about data. So the term for that is called metadata. This is data about the data. So how is the primary data stored? So how are the tables organized? What are the tables mean? What is the semantics of the table? What are the type of the table, etc., etc. Now one thing to note is that why is this being highlighted? Because metadata is accessed much more often than a particular piece of data. So whenever anything about the table is read, the metadata about the table needs to be written. So it makes sense to have some algorithms that can read the metadata faster. So it can be stored in a faster memory, for example, a particular, so it can be brought to main memory and persisted in main memory, because generally metadata doesn't change much. It does change a little bit about the statistics of the data, but the type of the data doesn't change much. So the metadata can be brought into main memory because it is accessed much more often. So this is all about the data. So of course what I mean to say is that statistics about the data is also maintained. So and that is all about this storage of physical design, and next we will cover the indexing.